I mean, you put the new card in.
You're on, yeah.
Test it a little bit. Okay, we're all here. So, introduce Don Thomas. Whose talk today is, what is it? Down.
Right there. Shutter and control.
Yeah. That's the talk, right. So, yeah. So, a little background here so you guys knew. Don did his undergrad in the dark ages, he says, okay? And then master's degree in surface chemistry, interactions with gas and solid surfaces in '72. He did his PhD here in volcanic gas geochemistry at UH in the late '70s. He's been doing, geothermal geochemistry, radon transport, isotopic geochemistry, groundwaters since through 1995. And then he managed the Hawaii Scientific Drilling Project on the Big Island, on the Hilo side, 3,500 meters deep, continuously core research on Hilo. So it's a very famous hole. And you guys already know this because you do all the readings, right? So, and he's currently working on research up in the Saddle area of the Big Island, so we'll talk about that. Kind of break some new ground and conceptual, more traditional models, shake things up a lot. Okay. Thanks for coming down.
Sure. Just the lights.
Yeah.
There we go. Okay.
Cool.
Okay, so I'll sort of begin with my ending. There you go. And essentially what I'm going to do is try to convince you of a lot of what you know about the hydrology of Hawaii is probably wrong. At least that's been the lesson that I've had to repeatedly learn as I've done these various drilling projects. And what I'm going to do is really talk about the currently accepted conceptual models for Hawaii's groundwater hydrology, and what do those models tell us about submarine groundwater discharge. This is kind of a cartoon that is frequently used, if not universally used, to describe groundwater storage and groundwater flow inside of Hawaii's volcanoes. The general concept is that we have rainfall recharge coming in over the mountain slopes, except in a few isolated areas where you have perching formations. That water will infiltrate down to the so-called basal freshwater layer, or will be sequestered in a dike complex and will be stored there and gradually leak out and supply this basal freshwater system. As the rainfall recharge that infiltrates in the interior of the island builds up ahead above sea level, that whole system will move towards the shoreline. This is what we can politely call a well-established model, but I take pains to point out that the model really was developed in the 1930s and 1940s and hasn't changed a hell of a lot since then. This is an image, and I assume, but I don't know if you're familiar with the reports that were done by Stearns and McDonald and others beginning in the mid-1930s. They did really an absolutely fabulous job of mapping the geology of the islands and interpreting the geologic mapping in the context of groundwater hydrology.
Don, if I could just,
Yeah.
I think you guys might not even know this, but we have all these reports from Stearns from back in those days, 30s on. And you may not notice, but when you walk down the hall and you see these geologic maps we have here, these are reproductions of the original maps that were done by them. So when you walk by, take a look, and you'll see up there it says, it doesn't say USGS, it says, probably territory of Hawaii,
Right.
water,
It's a geology and groundwater resources of picking them out. So they've got the geology and groundwater resources of Hawaii, of Maui, of Lanai, Kaho'olawe, and so forth.
But groundwater was a very central part of what they were doing in all of the context.
Well, and really looking at the history, this was heavily supported by the sugar industry, which was Hawaii's main industry back then. And they were tremendously reliant on groundwater, not only for irrigating their crops, but also for transporting the sugar overland to their mills. And so it was a critical resource. And so I will follow that up by saying that we haven't done anywhere near as good a job since then in terms of really trying to keep up with and characterize the groundwater resources in the state. And actually, we're trying to put together a program right now to apply some modern geophysical methods and modern geochemistry to reanalyzing the groundwater hydrology statewide. But their models, they did a hell of a job. They did a really good job. But so good that we kind of become complacent and not really improved on that model. So really our first hint that maybe we needed to go back and look at this model and maybe extend it a little bit was the Hawaii Scientific Drilling Project. And the project actually was conceived in the mid-1980s. We drilled a shallow test hole in Hilo that went down about 3,500 feet, and then with the success of that, we drilled the deep hole, and ultimately we got to about 3,500 meters. And the purpose of that project was to define the planetary processes associated with mantle plume volcanism. We were going to continuously core. We had hoped we were going to get to about 4 kilometers. We were going to go into a mature mantle plume volcano, being Mauna Kea. Mauna Kea has erupted probably 99% of the lava that ever will erupt. We're going to conduct geochemical analysis of the rocks recovered to see how the chemistry of the lavas change over the life cycle of a mantle plume volcano as it passes across the top of that mantle plume. And by the way, we were also going to take a look and see if there was anything interesting going on with the interaction of deep seawater circulating inside the island. The borehole located right here next to Hilo Bay. And this area here, as it happens, is covered by, actually from about here, this is all Mauna Loa lavas. However, this sort of slope break here actually marks Mauna Kea. And the location here is where Mauna Loa is encroaching onto the old Mauna Kea surface. And that brought us some interesting results. So this in a little bit larger scale. So we have sort of the Mauna Kea surface extending over here. This is Mauna Loa. And our drill site is actually quite close. It's within 3 or 4 kilometers of the intersection between Mauna Loa and Mauna Kea. But you have to remember, volcanoes on the Big Island, as it is on virtually all of the islands, is they are built sequentially. The oldest volcano on the Big Island is Kohala. Still a little bit of question whether Mauna Kea or Hualalai is next in line, then Mauna Loa, then Kilauea, and eventually we'll have Loihi. So Mauna Loa is banked up on the slope of Mauna Kea. Now, one of the unique aspects for Hawaii of that project was that we were not doing a borehole just simply to make the hole. We were after the rock. And so what we were using was a technology that has not been commonly used in Hawaii, diamond wireline core drilling. And with conventional rotary drilling, you have a much larger version of this kind of a bit. It's a tricone, and essentially these cones have carbide buttons on them, and their job is to grind up the rock, just make it go away. Okay, our bits are cookie cutters, And the cutting surface is a metal matrix that's impregnated with very small industrial diamond chips. As we drill, we leave behind this central core of rock that we are then able to recover. This is what we call a core tube. That actually goes inside the drill string itself. This piece here is lowered down and locks in behind the bit. As we drill, the core rises up in this steel tube until the tube is full. We stop drilling, we pick up the bit, break off the stub of the core, and then we send the cable down to grab the back end of this tube, haul it to the surface. We got another one that's empty. We get it going down, it locks in place, and then we're back to drilling again. So we don't have to recover the entire drill string every time we pull the core. So we then basically can unload that core. These are just the core trays to transport the core from our drill site into the processing lab. And when we're all done, we clean this core up, and then in this case, we split the core longitudinally. And so now you can do essentially hand specimen analysis of the core, and for this hole, we've got a complete geologic log from the surface down to 3,500 meters. And so what you get doing this is from garden variety ahoy hoy. Nothing special about it. You can see it in road cuts. Flows.
How long does it take to get to 3.5 kilometers?
Actually,
Recover all that?
the whole project took from start to finish close to 20 years. The actual drilling, 10 years was spent trying to get funding. The actual drilling, though, was done in less than a year.
So you kind of left that all out, which wasn't breath. You take a deep breath and look at that they want to appreciate the amount of time and effort that goes into it.
No, I actually did an analysis of how we spent our time on this project. 10 years was spent getting funding, 5 years was spent just doing permitting. 4 years was doing logistics and procurement, and less than a year was actually spent doing drilling. So why do we call it a drilling project? Anyhow, again, nothing special, but your standard lava flows. You can see where the gases have been squeezed out and so forth. However, we also saw some soil and ash layers, and these indicated that either we had some major eruptions nearby to lay down the ash, or these surfaces were exposed for an extended period of time. Now, these are, of course, subaerial lava flows. These are flows that have been laid down above sea level. Once we hit the transition from subaerial to submarine, characteristics of the lavas changed completely. This material is called hyaloclastite, and essentially what this is material that's generated when a lava flow comes in contact with the ocean. And it turns out that a substantial fraction of the island is built up of either the lava flows that have gone directly into the ocean, or these bench formations that collapse and form debris flows that flow down the submarine slope of the volcano. This, in fact, is how most of the volcano was built. Now, after that material has been buried for a while, it looks like this. It's become compacted. You have lots of seawater circulation going on. You have submarine weathering, and that submarine weathering also deposits secondary minerals and basically glues this back together to the point that it's pretty much like concrete. There are no pre-existing fractures in this core. When we pulled them out, they would just be long sticks. These breaks here were all generated as we unloaded that core. And had these very fine-grained materials. Again, it has the permeability of concrete. Eventually, though, we hit pillow lavas, and the pillow lavas are created when the eruption source, the vent, is below sea level, and it's far enough below sea level that you don't have violent boiling that will break up the lava as it's extruded. And so these flows, of course, they don't travel very far from the vent. They're chilled very quickly. You can see, if you look carefully, the glassy rims. And they're also shot through with internal fractures. And in fact, some of these fractures are open. So pillow lavas are permeable. This is my version of the life cycle of a Hawaiian volcano. You have the initial pillow phase. It's where Loihi is right now. As the summit of that pillow phase approaches sea level, you get violent boiling and formation of hyaloclastites. You get the even more violent hydroexplosions at sea level, and then eventually you start building up the subaerial lavas. But I've also tried to show that as this process is going on, the island is sinking. In fact, the interface for the HSDP hole between subaerial and submarine lavas was at a depth of about 3,600 feet below sea level. So we started at about 25 feet above. So that part of Mauna Kea has subsided by more than a kilometer since that first subaerial flow was extruded and laid down at that location. So what did we see with the groundwater? We saw something very interesting initially. We didn't really know what it meant. Okay, this is a temperature survey, and we see kind of these jogs in here, and this kind of this nose out here, and then the temperature falls off very drastically. This was a measurement made fairly shallow in the hole before we had gotten too far down. These, of course, these later temperatures were after the hole had been completed. My initial reaction was, well, gee, you know, this, I wonder if this is geothermal water coming from the interior of Mauna Kea. Well, it turns out that this nose, this increase in temperature is right at the transition from Mauna Loa to Mauna Kea. And at that transition, we had several layers of this kind of material, soil and ash, because that Mauna Kea surface has been exposed, we estimate, for between 100 and 150,000 years before Mauna Loa began encroaching on it. So thick layers, actually a series of layers of soil and ash had accumulated right there at that interface as Mauna Kea was sort of closing out, as it was approaching senescence. Fewer and fewer flows were getting to the distal edges of the volcano, and more opportunity for ash to be deposited and soil to accumulate. And actually, this is what our interpreted hydrology was in this area. When we actually went in and sampled, this is that temperature area where the temperature increased in the hole. That was fresh water. So we went through the Mauna Loa basal groundwater system into a bunch of sediments. It turns out that one of our drill locations was in a part of Hilo Bay, or an old Hilo Bay that had been partially filled in. So we went through a thick sequence of calcareous sediments into more fresh water that was trapped, Mauna Loa fresh water that was trapped below those sediments, into salt water. But then we hit that soil layer at the interface with Mauna Kea, and there was about 400 feet of fresh water at that location. The isotopic composition, I'll talk more about this later. The isotopic composition of the water that was passing through this system was much lighter than local rainfall. When I say lighter, it was isotopically lighter. And as it turns out, isotopically light water is from rainfall coming into Mauna Kea at high elevation. We can actually deduce the elevation at which that water hit the ground based on its isotopes. And it appears to have come from an average elevation, this water here, from an average elevation of about 7,000 feet on Mauna Kea. And it was about 2,000 years old. Can't see that very well, but again, fresh water from Mauna Loa, fresh water from Mauna Kea. And we know we've actually encountered, we did a pilot hole, as I mentioned, and saw this layer, and then in the deep hole, we saw it again. They're separated by about 2 kilometers, about 400 feet thick. We were able, estimating the distance to the 7,000 foot elevation on Mauna Kea, we were able to estimate the rate of flow of that water, and the volume discharging, we're estimating it somewhere in the hundreds of millions of gallons a day. So a substantial fraction of the recharge in this high recharge elevation of Mauna Kea is not being discharged at sea level, but in fact is being discharged at 1,000 feet or more below sea level. Now, just by serendipity, one of my cohorts when I was a graduate student was doing surveys using the deep submersible down this slope, and he actually saw evidence of freshwater deep discharge 1,000 feet below sea level. So we know that that system is active. It's not fossil water that's been carried down there. Of course, it's too old to be that, but we do see that discharge. We can't see it from the surface. It's not at all visible from the surface, but we do know that it's occurring.
And that's what he saw.
He saw temperature and salinity anomalies, and his explanation, he was an oceanographer, his explanation was, well, it must be freshwater discharge, but he didn't realize the significance of it at the time. He has about a 1-line mention of it in his dissertation, but I remember him talking about it when we were students. And actually, I'm getting ahead of myself, but I've been told that submersible dives over on the Kona flank of the island have also found deep freshwater, evidence of deep freshwater discharge as well.
And what would be the age of the water that's being discharged from the lower aquifer?
It's about 2,000 years.
And it's water that's going through the upper aquifer, and then there's leaking
no,
through the aquitard, and then...
No, what's happening is it's starting out as rainfall back here on Mauna Kea. It's infiltrating to whatever the internal water level is here inside of Mauna Kea. It's moving, and actually what I'm saying here is it flows radially outward towards the shoreline. But then it's essentially being intercepted, actually that should be intercepted, by soil and ash layers. And there is sufficient hydrostatic head within that internal saturated layer of it within Mauna Kea to push that water down below sea level and to force it below sea level to discharge as submarine freshwater springs. As it happens, that deep freshwater system also drives a saltwater circulation system. That's where you see that sharp temperature drop below the freshwater. It turns out that there is mixing between the fresh and the salt at that interface that drives a deep circulation system below the island of salt water. Okay. As I mentioned, as we got deeper below that subaerial section into the hyaloclastites, the compacted and indurated hyaloclastites served as another confining layer. And okay, this is sort of with the subaerial, the unconsolidated, and then the consolidated hyaloclastites, and then the pillows. And these pillows, turns out, are also carrying water. And it was a great surprise to us that when we encountered those pillows, they were also producing fresh water. And we were seeing fresh water within these pillow intervals down to as deep as about 9,900 feet. So we have sufficient hydrostatic head within Mauna Kea to displace seawater to below 10,000 feet. Now it's interesting that I believe, we have every evidence at this point to believe, at least in this area, that these are fully confined systems. They are in contact with the internal freshwater system inside of Mauna Kea, but they do not discharge to the ocean. When we allow these confined aquifers to flow, they would flow fresh water for some period of time, but gradually they would go saline and ultimately go hypersaline, so that the water was between 10 and 20% saltier than seawater. When we installed pressure transducers in the well with casing down to that 9,900 foot depth, we saw absolutely no tidal influence at all. When we were shallower than that, down to 6,000 feet in the uncompacted hyaloclastites, we saw very clear tidal fluctuation in the water within the well. But at 9,800 feet, we didn't see that at all. So these are fully confined aquifers, at least in this region. They're also highly pressurized. This is a photo taken at the rig floor. The drillers have just separated the drill string. Okay, one piece of the drill string is here, the other is here. And whenever they did that, they got a bath. Actually, as we were drilling in the deeper formations, we put a pressure gauge on the drill string, and we were seeing pressures in excess of 150 psi. So these things are under an extreme hydrostatic pressure. So the implication then is, in order to get fresh water down to these depths, we have to have much higher elevation groundwater within Mauna Kea than we had previously thought. Again, going back to the conventional guided Hertzberg model that we've all sort of grown up with, the assumption was that the water level, the highest the water level would be within Mauna Kea, a presumably very permeable volcano, would be only a few hundred feet high. That would not be sufficient to displace seawater to these kind of depths. And so that inference then led to a study of the Humuhula saddle, where we made some magnetotelluric measurements across the saddle. Magnetotellurics allows you to see the electrical conductivity of the rock, and you can actually see down 5, 10, 20 kilometers with this technology. And we started down here, which is located at the saddle, what's called the Saddle Road well. There's a water well, municipal water well here. And in fact, the water level there is 1,000 feet above sea level. But that provided us with ground truth as to what the electrical conductivity was of Mauna Kea basalts saturated with fresh water. And this is a cross-section through that surveyed line. And the electrical resistivity, or conductivity, resistivity is the inverse of conductivity, is about 620 to 1,100 ohm meters. Somewhere in that range is the resistivity of Mauna Kea basalts saturated with fresh water. And so what we see as we go across the saddle is areas like here and here, where the conductivities reach a kilometer to maybe 1,300 meters above sea level. Now, the resistivity doesn't guarantee you that you will find water at those elevations. The electrical conductivity is a function of saturation of the rock, but it's also a factor, or it's also a function of whether the rock has been altered by hydrothermal processes, whether it's actually pristine basalt or ash. So we do this. We have no guarantees that there's going to be water there, but we see these resistive formations that are upwards of 30,000 ohm meters, and we're pretty well guaranteed these are bone dry rock. So ultimately, we elected to drill a test hole here, and the whole idea was to really determine once and for all depth to groundwater within the mid-saddle region, determine the water quality, and try to develop an overall better understanding of the regional hydrology within the saddle. To my knowledge, there's only been one other hole drilled in the saddle. It was a rotary drilled hole, and it really didn't find much of use to us. We were funded to drill and test two, again, continuously cored, small diameter holes. This is some of what we found. We found sort of typical basalt, but we also found layers that were ash-rich and clay-rich, this sort of brick texture. And then we have difficulty preserving entirely the texture of this broken up material, but this brick-like surface indicates that this layer was very clay-rich. We also found some quite interesting things. The rock was actually fractured, and this is not how it was in the ground, but as we drilled, the rocks were breaking up into discs, which it turns out is quite informative for us. We got deeper, and we saw a lot of secondary mineralization, and we found dikes. Yes, ma'am?
How do you tell the difference between a fracture that you got during drilling and a fracture that was already in place?
Fracture that's already in place usually will have some degree of weathering. You have weathering processes and secondary either oxidation of the rock surface or deposition of low temperature secondary minerals on the pre-existing fractures. The fractures that are absolutely fresh and pristine have probably been created during the drilling process. But it is easy to distinguish between the two. And in fact, these fractures are characteristic of formations of rocks that are under very high horizontal stresses. Turns out that that is one of the characteristic indicators of highly stressed rock. And the dikes that we were seeing, we didn't see a lot of dikes, but we did see a fair number of them. Kind of explains why we were seeing those high horizontal stresses. So the geophysics indicated we ought to find saturation at 3,000 to 3,500 feet above sea level. We thought it was possible we would see some perched aquifers in sort of the shallower zones. And in fact, the shallow zone was pretty well dry. We did see a little bit of water at 500, but we saw a perched aquifer at 700 feet. It began at 700 feet below the ground surface. Now, the elevation from which we were drilling is about 6,400 feet. So we hit a saturated zone standing about 5,700 feet above sea level. And it actually extended for about 500 feet. And it turns out this is the formation, this is the rock that water level at 500 feet of water we're standing on. When we drilled through that, water level went away. Now let me, and I should explain this, I meant to do this earlier. Okay, I showed you the photo of the core tube that we used to recover the core. Now in these holes, we're drilling in unsaturated rock, so we have to lower that tube down on a cable. And of course the drillers are anxious to get back to drilling, so they lower the core tube pretty fast. And they can do that in an air-filled hole. As soon as they hit the water table, though, they got to slow down. Otherwise, they end up with a bunch of balled up cable. So it gave us an opportunity every time we pulled core to get a measurement of where the water level was in the hole. Now, the interesting thing is that we would see a water level that would hold stable in the hole, and so what they do is mark the cable and slow it down before they hit that saturated zone. But as soon as they drilled through it, then through the annulus, that water level is just simply going to go away. We're not going to see that water standing in the drill string. I hope that's clear. It may not be if you're not familiar with the technology. But anyway, once you're through that level, you don't have the hydrostatic head to push that water up the drill string. And they were able to see, once they got through this level, the water level inside the drill string was completely gone. That doesn't mean the formation was drained. It just meant that through the annulus, that water was now able to go into unsaturated zone below. Anyway, this will become more significant later on. But maybe a foot of core here. So a 1 foot thick layer of clay-rich ash was supporting an aquifer of about 500 feet thickness. This was a real surprise to us. We were in unsaturated layers below 1200, but then we hit a final saturated zone at 1800 feet, and the formation was continuously saturated from 1800 feet until we stopped drilling at 5,786 feet. That's the regional water table, I believe, within Mauna Kea. Totally unexpected. Again, before we started the hole, I suspected most people were betting I wasn't going to see water until I got down to 5,000 feet.
How are these relative to sea level?
Okay, 1,800 feet, you're standing about 4,600 feet above sea level. So we're starting at 6,400 roughly.
So
So
you
like
found
legitimately, go ahead.
I'm sorry, you found your purged aquifer somewhere around
Yeah.
6,000?
No, we
above sea
found,
level?
okay, the first aquifer, I apologize, I may need to clarify this. These are depths
Yeah.
below ground surface. Ground surface is about 6,400 feet.
64.
Yeah. So just subtract these numbers from 6,400, and that'll give you the elevation of the water table. You can legitimately ask, why are we seeing water standing in the saddle at 4,600 feet above sea level? This is just a little cartoon. This is sort of progress during the drilling. But one big saturated zone, a few sort of smaller zones of some saturation, and then continuous saturation. Again, from 1,800 feet. We stopped about 600 feet above sea level. And we were hoping to go to sea level, but one of the other surprises that we got in the hole was from about 3,000 feet, we started seeing the temperature go north, and by the time we got down to here, the temperature at the bit while drilling was about 100 degrees Celsius. Yeah. And the temperature gradient from 4,000 down to the bottom was about 165 degrees Celsius per kilometer. That's about 10 times the normal basalt temperature gradient. And that also kind of gives us a hint as to why we're seeing water at these elevations. Again, we go back to the old Stearns and McDonald model. This is a cross-section through Humaula, essentially the area that we were drilling. They were expecting water, no more than a few hundred feet above sea level. Again, the presumption was this was all very permeable basalt, and we would see a rise in the top of the water table of maybe a foot per mile as you go inland, more or less. considerably higher than that. Let me just mention the geochemistry and isotopic data indicates that the recharge into that 1,800 foot elevation water table is about 9,600 feet above sea level. Approximate age is almost 7,000 years, so it's pretty old water. There's also, of course, a strong signature of hydrothermal system in the deeper chemistry of the water. Well, the geophysical surveys show high-level water across the entire saddle region. There's evidence that it extends, is not just in this one location. Some recent gravity modeling was done by a student here by the name of Flinders, working with Garrett Ito. And they found evidence of a broad intrusive complex through the saddle between Mauna Kea and Mauna Loa. And in fact, we've kind of confirmed that because we did recover dikes. We did recover dike material in that area. And so we're postulating that we're seeing a very broad dike-impounded aquifer within the saddle that may actually extend over a big piece of the island. And so the indication is that we have a substantial volume of water stored at high elevations, and at the same time, if you consider the elevation of this water, it can also displace seawater to far deeper than what we saw in the HSDP hole down here. So the indication is that there's a hell of a lot more water here than we had realized. So we elected to test the hypothesis with a second hole. It's probably my first mistake. We were looking at this conductive anomaly extending sort of out to here. As it happened, we were able to drill right here, just beyond that conductive anomaly, right about here. It's in that sort of triangle made by the old saddle road and the new saddle road. You may have seen my rig up there. We were going to try to define the western extent of the aquifer. And, excuse me, currently we're at a depth of about 4,500 feet. We're not done with it yet. We have another 1,000 feet to drill. But we had a very different sequence than what we found in the first hole. Whereas in that first hole, we found perched water table and then the regional aquifer. We actually encountered a sequence of confined aquifers. We were drilling in dry hole down to here, down to just below 1,000 feet. We drilled into an aquifer, and where before water level held stable, when they drilled into it, they pulled the core tube, they went back down, and they had 20 feet of water in the hole. They drilled another 10 feet, sent the tube in, and they had water standing at 600 feet in the hole. So we drilled into a confined aquifer that was under substantial hydrostatic head, and when we pulled the core tube, essentially the hydrostatic head within that aquifer was able to force water up to within about 400 feet of the surface. And in fact, as we continued drilling, we got down about another 100 feet and the water level went away again. So we drilled through initially a capping formation and then subsequently drilled through the supporting formation. And when we did that, we lost that hydrostatic head to drive the water up to the drill string. So the water dropped back to the bit until we hit the next one, and the next one, and the next one, and the next one. And that's what we saw for the balance of the hole from a depth of about, 2,000 feet until we stopped drilling at 4,500. And this is the great thing about doing hydrology on a core hole. You can actually see the formation that's responsible for the water that you've encountered. Okay, this is where we hit that pressurized zone. See a very clay-rich layer here. I don't know for sure what the source of it is. We're still in the process of analyzing the core. But this is that capping formation. This is the supporting formation. So we're able to go and look at the core and see what the rock looks like where we see a change in the water level. One of the interesting things actually in this one, makes for interesting drilling. When we hit this system, the water rose about 1,000 feet in the hole, and in the process it actually lifted the drill string. That was something that you don't see very often. Didn't cause us any problem, but it was a bit of a surprise for the drill. But even down here, at about 4,400 feet, we had water rise in the drill string to within about 800 feet of the surface. So that's about 3,600 feet of hydrostatic head. So what's my point? Oh, by the way, this is the formation that was capping that layer. Okay, this is very interesting. Okay, we've got a breccia zone that's mixed with ash. It's either very highly consolidated or possibly was laid down hot enough for it to be welded. We don't know what the source of this ash is. Obviously it could be monocap. But a paper was done some years ago by Pete Lippman looking at sort of the surface topography of Mauna Loa, as well as the bathymetry offshore of Mauna Loa. Mauna Loa has experienced at least 2 massive landslides. And Lippman proposed that perhaps one or both of these slides unroofed Mauna Loa's magma chamber and actually sloughed off a significant section of Mauna Loa into the ocean. You'll have to read his paper. I don't want to get too deeply into that. But if something like that did occur, it could have laid down a blanket like this. Anyway, we will be analyzing the chemistry of the clasts in here to see what volcano they likely came from. This could be a very interesting finding for us. We actually did see a similar breccia layer in our first hole as well. We're not sure whether we can tie the two together or not. But anyway, very interesting. But my point is that we've got these confining layers inside the volcanoes.
How many are in there? Every one of those lines is representing an individual line layer, is that correct?
Yeah.
You got like a red zone between each one?
Well, we're seeing ash or clay-rich zones. But we're not done analyzing the core yet. I mean, that's one of the things that we're in the process of doing, is looking at the rock where we see this jump and then the loss in the water level in the hole.
And it's all relic, do you think, or is it connected?
Well, that's the question. We don't know. I mean, it's, whether all of these are connected or not. I mean, when the water level drops, the water level seldom stays at that elevation. So clearly, these things are separated from each other. So we see the water level rising and falling as we drill.
The big mystery is what's happening.
Well, exactly. That's really the question. We appear to be outside of the dike system now. We have only seen a few dikes, fewer than we saw in the first one. The temperature is also significantly lower. But the bottom line is we're seeing a sequence of these confining formations that clearly are intercepting groundwater from higher elevation And they're either storing it if they pinch out, they're storing that water, or they're going to control how it flows and how it interacts with the nearshore groundwater system. 'Cause if you can envision, okay, we're at about 5,400 feet elevation for this hole. Okay, if you follow those formations all the way down to the submerged shoreline of Mauna Kea, then those confining layers could be discharging water at 3,000 and 4,000 feet below sea level. So we have kind of two cartoons that we've been working with. Okay, one is that we've got this dike impounded groundwater system, and a question of sort of how far out from the center of the volcano these dike systems are able to confine water. But we also have this question, okay, well, if we have these multiple confining layers, then, is this water being discharged well below sea level? And it has significant implications for the water supply that we are relying on in the coastal environment. So the question is, do we have any evidence that these confined aquifers extend to the shoreline? By the way, tell me when I'm running out of time.
Oh, you got
Plenty of time.
plenty of time.
Okay, great. In fact, we do have evidence that we have confining layers that are intercepting and sequestering fresh water down near the shoreline. This is a salinity and temperature profile. I'm going to concentrate on the salinity profile here of a test well that was drilled in Kona. It was a Kamakana well, and the salinity profile was drilled at two different times. The green line here was drilled, or was run April 3rd, and this was the depth of the well into the groundwater system. 0 here is the top of the water table. And what you're seeing is salinity being relatively low when you immediately intercept the basal groundwater system at that location, but very quickly it goes saline with depth. And by the time you're into that water table to the depth of 500 feet, basically you're in seawater. And that water stays saline down to 950 feet. Well, about a month later, a little over a month later, they had continued drilling, and the salinity profile now looks like this, where this area here, of course, is about the same, but what we've got down here at about 1,050 feet is we've hit a horizon saturated with fresh water. Okay, that fresh water is more buoyant than the seawater, and so what it's doing is it's coming up the hole. Salt water is entering the hole here as well because you've got a lighter water column, and so it has a hydrostatic head above sort of the mass of that water column, or the density of that water column. And so what you're doing is you're sending a mixed fresh saline water up that's discharging out of the wellbore at a depth of about 175 feet below the water table. So what we're seeing here is fresh, salt, fresh, with clearly confining formations here holding this freshwater system. There's another well in Kona, the Teoku Deep Monitor well. I don't have any profiles in there. The profiles are pretty boring, but there's a video, and I didn't think to bring that with me, but the video shows massive upflow. It drilled into the freshwater system, into salt water, but then back into another freshwater layer. And that freshwater layer is probably producing 300 or 400 gallons a minute up the wellbore, essentially pressurizing the entire wellbore to the point where it's all fresh but you've got deep fresh water coming up and then discharging into the shallower freshwater system. And the isotopic data in many of the wells in Kona show a significant divergence from what you would normally expect for groundwater mixing. Now, I'm going to give you kind of a primer on isotope geochemistry of groundwater in Hawaii. Okay, so conventional model, rainfall infiltrates, the water essentially goes down to the basal lens and goes out to the ocean. So here we have the Kona slope. This is essentially a transect from about 15 kilometers offshore of Keho up to 15 kilometers onshore, just about where Kailua is. And we can first postulate that we've got our conventional Guyvan-Hertzberg lens, fresh water, and we have rainfall recharge. Now, what I've tried to show here is the length of these arrows corresponds to the annual rainfall. So the average annual rainfall near the shoreline is quite low. As you move upslope, though, you see significant increases, and within this region here, you have your major recharge coming into the Keho groundwater system. I've also tried to depict the change in the isotopic composition as we go inshore. The rainfall nearest the shoreline is what we call the heaviest. It is enriched in the heavier isotopes. I'll explain this in more detail in a minute. As we go upslope, it becomes progressively lighter. In theory, then, if we sample the water here, it should be a mixture of all of the rainfall occurring upslope. Now, I've taken some liberties here. There are other processes that assumes that this is a well-mixed aquifer. So what's the big deal? Why am I interested in the isotopes? Not all rainfall is identical. Okay, everybody knows, or I hope you know, water molecules consist of one oxygen atom and two hydrogen atoms. But not all oxygen and hydrogen atoms are identical. Okay, how many of you are familiar with isotope chemistry? Okay, fair enough. Good. So we have O18 and O16. We have hydrogen, deuterium, and tritium. Tritium we won't worry about. So what? The water molecules containing the heavier isotopes of oxygen and hydrogen have a tendency to condense slightly more efficiently. Their vibrational frequency, their molecular internal vibrational frequency is slightly lower for the heavier isotopes. They condense slightly more efficiently. And so as marine air moves onshore, the first water that forms is going to be slightly enriched relative to the moisture in the cloud. It's going to be slightly enriched in the heavier isotopes. As that cloud moves further and further up the slope, it will become progressively more depleted in the heavy isotopes. And likewise, the rainfall that is generated from the cloud will become progressively more depleted in the heavier isotopes. So rainfall at the shoreline will be slightly lighter. This negative number indicates it has a lower concentration of oxygen 18 or deuterium than ocean water. Everything is relative to ocean water. As it moves upslope, it becomes significantly lighter. This is a line, this is from Joe and Craig's work, where they have collected rainfall at various elevations and determined the isotopic composition of the rainfall over, how many years do you have? 2 years of data?
3 years.
3 years now.
Fluctuations, but 2 for me.
And it follows reasonably closely a straight line where the isotopically heavier is closer to sea level, elevation in meters. You can see significantly lighter rainfall at higher elevations. Okay. So, if we sample the groundwater, what we should see is the volume-weighted average of the rainfall occurring above that source. Essentially, isotopic value is the mixture of the isotopes of all of the water coming into the system. So what I've done here, what I'm showing here is, okay, this number is the rainfall rate, annual rainfall, elevation. And this is the approximate isotopic composition, the annual isotopic composition of that rainfall. So we see from -3 to -5.4 at an elevation of 1,800 meters, a little better than 6,000 feet. If we don't see that, then that tells us something else is going on. Okay, in the Kehoe Aquifer, we've got wells that are classified as high-level wells and basal wells. Again, in theory, the isotopic composition of the water in these high-level wells should reflect something that's consistent with the rainfall that is falling within this region and above, whereas the water at this elevation should consist of the volume-weighted average of rainfall from near sea level all the way up. Without going into too much gory detail here, it doesn't. Okay, the lower elevation wells, you're seeing -3, -2, -4. So, again, not an unreasonable average. -3 here, -3. However, when we get to the high level wells, we're seeing -6.8 roughly, -7, -7, substantially lighter rainfall here, even though the local rainfall, the majority of the recharge is occurring within this region, and its volume-weighted average, I'll get to that in a minute, its volume-weighted average is around -4.7. So this water is substantially lighter than the rainfall that essentially fell above. Okay, talk about that in a minute. We're now working with 2 models for the groundwater system to explain why. Let me back up, I forgot to mention one thing. Okay, the elevation, this is called high level water because down here the basal groundwater system is only a foot or 2 above sea level. The heads in the groundwater table, a foot or 2 or 3 down here. Up here, they're 100 to 200 to 300 feet above sea level. So we have a very sharp transition from sort of a very thin basal groundwater system to high level water. One working hypothesis is that, okay, that high level water is associated with a dike system that is essentially sequestering that high level rainfall behind the dikes and gradually allowing it to leak into the water table. And if that's the case, if we apply our model here, volume weighted average of the rainfall within the highest recharge area is minus 4.3. Yet, the water that we're seeing in the wells in this high level aquifer are around minus 7. If we take all the volume weighted average all the way up to the summit of Hualalai, it only gets up to minus 4.7. So this, the high level water is showing tremendously different isotopic composition than what it should have. Okay. Again, you can see that. Again, substantial divergence here. In order to have that reservoir of minus 7 water within the dike compartments, we'd actually have to add additional water that's isotopically lighter, essentially of equal volume to all of the rainfall in that area. And that water would have, that water that we need to add has a volume weighted average of minus 9.3, which says that it would have to come from an elevation of about 11,000 feet. Okay, Hualalai is not 11,000 feet high. And even if you had water coming in from Mauna Loa, there isn't a heck of a lot of rainfall coming into Mauna Loa's slopes at 11,000 feet and above. So it gives us kind of a problem here. We also sampled C14 ages in those wells. Found two interesting things. One is it was pretty old. So that water in the high level wells, in 3 of them anyway, or 4 of them, averaged about 3,000 years. In 2 of them, it was even older. However, these wells, this is the other interesting thing. The carbon dioxide from which the age was determined shows evidence of contribution from magmatic CO2. So apparently Hualalai is also degassing. So there is some CO2 discharge into the local water table from Hualalai. As it happens, magmatic CO2 has an infinite age, basically. It has 0 carbon-14 activity. And so dilution of atmospheric CO2 contained in the groundwater with that old, very old magmatic CO2 would explain these much greater ages. It's also isotopically different, and these waters showed isotopically different values as well. But again, within that dike-compounded system, if we have recharge coming in, it's a little bit difficult to understand how that water could be that old. And if we're pulling water from the top of that dike compartment and we had recharge coming in from above, the vertical hydraulic conductivity is probably on the order of a few hundred feet per day. So very likely that we would see substantially younger ages if we were getting that surface recharge from the immediate vicinity of these wells. So what I'm proposing is that we've got something similar to what we're seeing up on the upper slopes of Mauna Kea, is that we have a sequence, one or more, don't know because we haven't core drilled any of this area, but we have ash or possibly trachyte confined aquifers here that are intercepting recharge coming from upslope and intercepting that water, diverting it away from the basal lens. We know that that nearshore basal lens in Kona is somewhat starved. It's thinner than it should be if it's receiving all of the recharge that's occurring upslope on Hualalai and Mauna Loa. so these aquifers, or these confining layers are redirecting that water into the ocean, offshore at depth where we can't see it, and depriving the coastal aquifer of recharge. We do have some through aquitard loss, but again, using our conventional model for infiltration, this doesn't work. Okay, we can't have infiltration coming in, but sequestration or confinement going horizontally. So what we probably have is a system where these layers may not be, perfectly tight, but what they do tend to do is divert rainfall recharge. The isotopically heavier, low elevation recharge is being diverted down into the coastal aquifer. The higher elevation has more opportunity to infiltrate and be intercepted in these high-level aquifers. And so we're getting some recharge, and there was a study done by Kelly, what's her last name?
Or Jackie Kelly.
Jackie Kelly, that's it.
Kelly.
Right. That looked at CFCs and found some CFCs in these high elevation wells, but not very much. I think what she was estimating 85 to 95% old water in these high elevation wells and only 5% underwater. Maybe that was what was in the thesis anyway. So there is some opportunity for this local recharge to get in, but the majority of this recharge, isotopically heavy recharge, is actually being redirected down into the coastal aquifer. And the higher elevation water is, again, being redirected away from the coastal aquifer and into the ocean. And again, if you can envision the boreholes like the Kamakana well drilled into the basal fresh water, into salt, and then encountering a second layer of fresh water, that would be consistent with what that Kamakana well saw. Likewise with the Keopu deep monitor well, through the fresh water, into salt, and then back into a very productive freshwater system. Isotopically, okay, the Kamakana well, this was an analysis, isotopic analysis of the water coming up from depth in the Kamakana well, minus 6.57, very similar to the high elevation water. And likewise with the seaworm deep monitor well, minus 5.5, looking very much like this high elevation water. Okay. So the underflow is consistent with Kamakana and Keopu. Talk about that. The bedded confining layer can also act as a perching formation. And we did have an opportunity to sample perched water. The Como well was cased above a perching formation. There was water coming into the well from below the casing. We were able to get a sample of that, and it looked very much like the isotopic composition of the local rainfall. It was much heavier than the deeper water in the high level aquifer. Okay. But it still requires that we are getting recharge into that high level aquifer from on the wall, because it is isotopically very low. So, how does it relate to the other islands? Well, we don't really know. And we have not traditionally done core drilling. We haven't really looked at the hydrology in detail. We've got models that are generally accepted. But when we try to apply them in sort of very localized areas, we're finding that they don't work very well. Nonetheless, we can reasonably infer that the volcanic history of each of the volcanoes, as well as another factor, which is the island's subsidence, will play a very strong role. Basically, my argument is that until we understand in detail the volcanic history, it's going to be very difficult for us to understand in detail groundwater flow and understand what fraction of the high elevation recharge is making it into the coastal aquifers and what fraction may be bypassing those coastal aquifers and being discharged at depth in the ocean. This is just something that I don't know if other people have talked about in other classes. Okay, this is the bathymetry for the Big Island. Okay, here on Kilauea and Mauna Loa, which are sort of actively growing, we have this very sharp slope break, but when we get to Mauna Kea, we see this sharp slope break well offshore. Okay, my argument is this used to be the shoreline of Mauna Kea, as these used to be the shoreline of Hualalai and Kohala volcano. So we're seeing significant subsidence even in the volcanoes as young as Mauna Kea. And you have to think about this in the context of, okay, we've got sort of the submarine transition right here at the shoreline here. Here in Mauna Kea, as you move to the north, the transition from subaerial to submarine, and the transition from sort of the very open hyaloclastite to the consolidated and indurated hyaloclastite is actually sinking. That's going to affect how both seawater circulates through the system as well as how the groundwater system is interfacing with the deeper submarine seawater. We look at Maui, and that transition now is about 2 kilometers deep. So the island of Maui, Maui Nui, has subsided by more than 2 kilometers. Okay, all of this was at one time subaerial, and hence will be the Hoi Hoi and A'a lava flows, highly permeable, perhaps somewhat compacted, similar to what we saw within the deeper parts of our first borehole up in the saddle. Because we do see compaction as we get down below about 4,000 or 5,000 feet. But still highly permeable formations out here. And if there are confining formations, then it's not hard to imagine that recharge entering the system up here can be discharged down along these submerged slopes. And same story with Oahu. And it's interesting that Oahu is not subsided by significantly more than Maui has. This transition zone here is, I think, about 1,800 meters. 1,900 meters, something on that order. Of course, the other factor that I didn't mention for Maui, okay, this is also part of the Nu'uanu landslide. And of course, that's going to affect how whatever groundwater, saline or freshwater system interacts with the ocean here as well. Okay, take home. We have strong evidence for significant aerially extensive confining formations that are buried within the volcanic structure. And both in the subaerial and the submarine stratigraphic section. Those confining formations affect both shallow freshwater circulation as well as submarine groundwater discharge. And the good news is there's much higher volume of water stored inside the islands than we had previously thought because of that. But because the groundwater system is compartmentalized. A lot of our assumptions about the sustainable yield for these individual aquifers is probably incorrect. And they may very well be overestimates. Conventional way that groundwater systems are managed here in the state is that sort of we have these pie wedge shaped aquifer systems. We aggregate all of the rainfall that hits the ground within that defined system, and usually that aquifer system is, the boundaries are defined by surface geology, not subsurface geology. And basically, it's assumed that we can withdraw, say, up to 40% of all of that recharge without substantially compromising the water supply within that aquifer system. But if a substantial fraction of that water is being intercepted up Malka and is being discharged into the ocean, then we don't have access to all of that recharge. We only have access to a fraction of it. So I guess I should add a final bottom line is that in order to manage these resources, we really need to better understand them so we know exactly how much water is available to us for our use and how much is we are required to leave in the ground for natural processes. Okay, I think that's it. Thank you. So, questions?
Why are you guys so surprised at your findings? I mean, my initial thought is looking at this stuff is like, geology is going to be really complex. So these sort of these simplified models that Stearns and McDonald have come up with, why is everyone just taking them so sort of like face value? Okay, this is what we have, and then all right, let's move on and focus elsewhere.
Basically, because when Stearns, this is my opinion, Stearns and McDonald did a hell of a job, and lots of students have gone out with the idea that they were going to sort of add to the geologic mapping and so forth that Stearns and McDonald have done. And usually come back to find that they really can't improve on what they did. I mean, they did a really good job. And
But at the surface level, right?
And the surface, and sort of take that one step further, most of the wells that have been drilled in the state have been drilled near the shoreline. There are like 4,500 wells that have been drilled in the state. Most of them, the majority of them, were drilled near the shoreline, and nearly all of them, with the exception of the ones that I've been directly involved in, I don't know of many that have been core holes. And with rotary drilling, a rotary rig drilling where we're currently coring, if they'd been drilling the hole, they wouldn't have seen any of those confined aquifers at all. They wouldn't have known they were there. They would have just blown right through them. And because they have no way to test the water level in the well on a regular basis while we're drilling.
There's some fairly rapidly growing communities on upslope Hilo. And based on what you're showing us here, one might think that there would be access to water based on this geology of these confining layers. And in your opinion, would it be worth the people of those communities to pitch together and drill a well?
I think so. I mean, my feeling is that okay, every well that we've drilled, we've had a big surprise. The thing is, though, that when you're drilling, you have to be aware that these confining layers may be there. And there isn't broad sort of recognition of this kind of stuff. You know, everybody was kind of excited when we found the artesian system there in Hilo. They do see in that Saddle Road well that I mentioned, They do see high level water there. But I think the assumption was that, well, this just must be dike, somehow dike confined water. They still had to drill 1,000 feet down. But we haven't really drilled in a way, and one of the things that we're trying to do is see if we can get some hints on this using geophysical surveys. I mean, this is not an inexpensive exercise. To drill one of these holes, and especially like to the depth that we're drilling, you can figure on $500,000 to $750,000. It's not inexpensive. And really, what I'm doing is really just sort of identifying that conditions are different than what we thought they were, but I sort of don't have either the charter or the funding to actually test these things in as detailed a way as I would like to. And what I'd really love to be able to do is go in, case this hole, and perforate each of these horizons and look at the pressure of the hydrostatic head in those horizons individually and sort of see if they're sustainable or not. But that's sort of a whole other order of magnitude increase in cost of this exercise.
John, you were contracted by the Army.
Right, yeah, the Army
So what's
supported
the
this.
success story for them for the water research?
Well, they're ecstatic because water at a couple of thousand feet, they're spending $1.5 million a year to haul water to the Wakawa training range. It'll cost them maybe $2 million to drill and equip a production well for their use, and probably reduce that number to 10% of what it is now.
Are they gonna do it?
Yeah, their plan is to go in and drill a production hole. Yeah, I mean, it makes perfect sense. Their payback is like 2 years, and they've recovered what it cost them to put in the
What
well.
kind of risk would you say that it would go dry?
Well, I mean, we did a pump test on that deeper aquifer, and on the aquifer at the 1,800-foot depth. And basically, we can't do, again, we're dealing with a 4-inch diameter hole, and that was, the pump test itself cost me a couple $100,000. But getting a pump into that small a diameter hole that can lift water 2,000 feet is not an easy or routinely done exercise. They would drill like a 10 or 12 inch diameter hole, but we pulled 42,000 gallons out over about a 36-hour period, and we got a drawdown of about 10 inches. So we are not seeing a huge drawdown. It's not like we're in a little tiny compartment. So I think they have a pretty good shot at being able to drill a production hole successfully.
So the aquifers at Saddle Road are deep enough that their bombing exercises aren't likely to affect them either.
No, and again, we're seeing these perching formations, which appear to be intercepting a lot of the water. And where we're seeing that water coming from isotopically is upslope.
Yeah, I was just thinking of like fracking.
Oh, no, that would be much bigger bombs than they're using to affect that.
Maybe we would do some good.
Can you estimate the base flow depend on isotope signature?
Again,
Can you estimate the base flow depend on isotope signature?
Not really so much on the isotopic signatures. The way that we looked at the flow rates was to look at the age of the water and make an estimate of sort of the thickness and extent of the aquifer. Is that answering your question? I mean, we were looking at the total volume of flow going through that helo system. That's how we calculated it, or estimated it. And at best it's an estimate because we've got 2 points that are more or less oriented perpendicular to the direction of flow. But it could be much more extensive than what we saw. I don't think in either hole, we were at the full extent of the aquifer. Actually, it kind of, for me, it was interesting that back in the near dark ages when I was a student here, I took volcanology class with Gordon McDonald. And interesting turnabout, we were on a field trip to the Big Island and we were talking about the groundwater. And he told me at that time that still the hydrology was a puzzle because they could sort of make a reasonably good estimate of what the recharge was, how much water was going into Mauna Kea. But then when they did the inventory along the shoreline, he said basically there's nowhere near enough water coming out of the island to account for all of it that was coming in with the rainfall. So he knew even then that the picture wasn't complete. And this deep underflow is how we can account for that, the divergence in those two values.
Really gets submarine.
Well, that's something I would really like to do, is to see if we can come up with some cost-effective way of surveying the submarine slopes that would allow us to make an estimate of what that submarine discharge actually is, the deep submarine discharge.
I want to ask a question a little bit off topic. Where does the hypersaline water come from that you encounter?
Now, the hypersaline water is interesting. Chemically, it's quite different from seawater. And it turned out that when we saw that water, I went sort of thrashing around trying to find analogs. And it turned out that there were some French researchers had drilled boreholes in French Polynesia where they had a thick sediment layer. They drilled through the sediment into the underlying basalt. And essentially they found hypersaline brines down there. And they postulate that what's happening is, again, you're dealing with pillow lavas. Pillow lavas have lots of glass because the lava is chilled very quickly. One of the processes of submarine weathering is that glass is unstable. And the first step in the breakdown of glass is hydration. So the glass begins to take up water. And essentially what's happening is it's sucking water out of the seawater that's trapped there. Same time, you've got chemical reactions going on. In our case, the water was virtually totally depleted of magnesium. And the magnesium, I believe, was being taken out, essentially taken up in clay formation, low temperature clay and zeolite formation. But the glass is very reactive and it does break down. And so you end up substantially changing the composition of that seawater.
Was theirs also really depleted magnesium?
Yes, yeah. Very similar chemical composition.
Was that they had a thermal pump that was driving water through it?
I don't recall if they, had postulated that there was thermal activity, because it was well away from sort of the spreading center that had generated the crust. I mean, this was water, or
They were
surface.
up on an island.
No, this was in the ocean. This was deep ocean drilling. So this was ocean drilling where they were offshore, drilled through a thick sediment blanket into the ocean crust.
Oh, okay.
And that's where they were seeing this hypersaline brine. See, the sediments
Yeah.
are sealing and isolating that water from circulation back into the ocean. That's actually another aspect of what's going on with around these islands, because the older islands, of course, have developed significant sediments. And so that's going to have some effect, or may have some effect, on circulation of ocean water in under the island, possibly even could impede the discharge of fresh water as well. I don't know.
That kind of, I have a question for myself was, so do you think there's a hydrothermal circulation involved here in Hawaii as well?
I mean, certainly there is an opportunity for hydrothermal circulation. One of the interesting things I didn't, although I showed it, let me go back to it. One of the surprises that we had with the Hawaii Scientific Drilling Project was, how cool. Okay, here we are at 3 kilometers depth, and we're only about 45 degrees Celsius. That's not hot at all. The temperature gradient down here is only about 17 degrees Celsius per kilometer. So a very low temperature gradient through here. I don't know why this thing isn't. But that gradient, what I understand is, and I'm not an expert by any means in this, but I'm talking with guys that have done work in basaltic crust and oceanic crust. They've told me that the typical gradient away from the spreading center is about 17 or 18 degrees Celsius per kilometer.
And what is this?
This one, okay, in the HSDP, this was about 17.
That's okay.
It's about 17 per kilometer, whereas in the saddle, in the hole there, it was 165.
Right.
So, away from a heat source, you have a very, very low temperature gradient.
Right.
And that's an indication of a strong seawater circulation?
No, actually not. That is sort of the conductive gradient. That was one of the, again, another piece of this was, you have a relatively flat gradient here, and this was sort of after the hole was fairly well stabilized. Okay, there's lots of circulation in here, because any heat that's generated, seawater is coming in and sucking it out. But down here at about 1,400 meters to 1,500 meters, we see then a transition to a progressive increase, but a very gentle increase, and that's that 17 degrees C per kilometer. And that basically is the conductive gradient, where you don't lose a lot of heat by water circulation. And again, that's where we were in that indurated hyaloclastite, where we didn't see much.
In my mind, I keep thinking it's a bigger scale, so I think about, what's happening off the flanks of the ocean ridges, right? Because all that water is coming in, sucking up all that heat, it's
Right.
way out there, way away
Right,
from
yeah.
the major heat source.
Right.
It's similar.
But the thing is, though, with the mid-ocean ridges, it's all pillow basalt. And,
But no, I mean, it's going way deep. Right?
yeah. But here, okay, these hyaloclastites, because they're so tight, pillows are gonna be fractured.
Yeah.
These are tight, and the way I envision this is that essentially the base of the island is like a big inverted bowl. But, you know, we've got a core of pillow lavas that may be fractured, but then we've got this drape of indurated hyaloclastites that essentially cover those permeable rocks, so that, you know, you don't have circulation coming in from the deep ocean.
It's like a checkered layer.
Yeah.
And you're referring to depths below about 1,200 meters then?
Well, yeah, actually around 1,400. And it was right around 5,000 feet, where, see, we were drilling through, let's see, so, you know, about here is where we hit the end of the subaerial rocks. And from here on down, we were in complete mush, you know, for about 1,000 meters. Excuse me, about 500 meters, something like that. Anyway, and then it got to be fully indurated and just very little water flow.
All right, so for you guys that are like these submarine groundwater discharge experts here in the room, does that mean that freshwater discharge somewhere between 800 and 1,200 meters is driving strong seawater circulation in? Is that the hypothesis?
No, what's happening is that at this interface right here, this is where the fresh water is discharging, right here.
Okay.
And what actually happens, and if you're interested in sort of seeing a detailed discussion of it, Clifford Voss wrote a nice paper. It's probably 15 years old now at least, for Oahu, where he was postulating that, okay, you have that freshwater flow discharging from the island. You've got the interface of an active freshwater system with sort of a more stable seawater system. You have a chemical gradient for the dissolved ions in the seawater and the fresh water, so that chloride ion, sodium ion, and so forth diffuses up into the fresh water and ultimately causes mixing of seawater with what had been fresh water in that transition zone. And the upshot is that some of that seawater at that interface is being carried out. It's being flushed out, okay? Conservation of mass, if you got seawater leaving here, you gotta have seawater coming in somewhere else to replace it. So that was how he accounted for the seawater circulation system, because, okay, if you think of it as two water bodies sort of moving next to each other, okay, you could conceivably generate some shear between the two, but you can't do that in a solid. So you have no way to transfer momentum from that flowing freshwater layer to what would otherwise be a static seawater layer. And so what he was postulating was, because of that chemical gradient, again, doing the thought experiment that if that seawater never moved, eventually the salt would be completely depleted from it by that mobile freshwater layer. So he was saying that basically that was generating a mixing zone within the transition that ultimately led to seawater being carried out with that freshwater flow.
Thank you for finally saying that in a way that makes sense.
Ah, okay.
Because I've always, heard, oh yeah, there's salt water seeping in through here, and it's like, why though? Like the physics of it never made sense to me until now.
That's, again,
That's
Cliff
little.
Voss goes into detail on that. Yeah, no, it took me a while to kind of get so I had a sense for how it was working. But yeah, you can't impart momentum where you have
Like the
the
pore
interface
space.
of pressures. Right.
Even with conductivity, I mean, the fresh water can't escape the island without some sort of conductivity coefficient. I mean,
Without,
that should be permeable to some extent.
Well, yeah, it is permeable. But again, it can't, how does it impart momentum to the salt water? How does it mix? Yes, sir.
Why the top layer is not affected by the cold groundwater? Called the fresh water.
Why, I'm not sure.
Look on the diagram.
Okay, in here, you've got a bunch of stuff going on in here. Because what we're doing is we're drilling through unsaturated rock at the very surface, then into a water table. But it's the sort of coastal groundwater system, basal groundwater system of Mauna Loa. So that's kind of what we're seeing here. And we're seeing mixing in here with seawater. And then we're in that transition from Mauna Loa to Mauna Kea. So you got a lot of stuff going on in there. And actually, I mean, in these, what you're seeing is actually flow to the surface, this yellow curve. Okay, we've actually got massive fresh water flowing from here up to the surface. When we actually drilled into that zone, we were producing about 2,000 gallons a minute artesian flow out of the hole. So I mean, it was blasting up there all by itself. Unfortunately, we're not able to get a good measurement of the hydrostatic pressure within this zone, because when it was flowing, I mean, we actually, this caused us a problem while we were drilling. We were down in an old quarry and we damn near flooded ourselves out. I mean, we had water sort of rising fast, and we had a guy on a backhoe trying to find a trench to build a trench to get it away from the rig. So we were desperately, we had no way to shut it off. We didn't have a wellhead valve on it, and we were scrambling. So eventually we did get it shut off, but we didn't get a good measurement of what the hydrostatic head was in that zone, because we had several hundred feet of open hole. So it was able to bring water up to the surface, actually to an elevation of about 35 feet above sea level. But we were also losing lots and lots of that fresh water out into the exposed formation in the uncased section of the hole. So it had plenty of head behind it. I've had easily a dozen people ask me about bottling that water. Everybody here is 2,000. Actually, when we hit it, I mean, there's Fiji water was selling for
Yeah, man.
whatever.
Oh, no, but it's, it's ancient water.
Right. Well, theirs is only 500 years old, and our water hit the ground before the first human set foot on a big island. So, guaranteed pure. Nobody's ever been able to make business out of it.
So can you say in short what are the main stratigraphic controls now? Like despite hydrostatic head and confining layers, and what?
Well, I mean, this is a thing. It's going to be unique to each volcano.
Yes.
And so, if you have, say, let's say within a volcano you have a sector collapse event that generates massive pyroclastic flow that covers 200 square miles of the subaerial volcano, and subsequently then buries, with continued activity, buries that horizon, then that's going to be a confining layer. But it may not be, and certainly in our case with the drilling that we're doing up there, those formations are probably not exposed at the surface anywhere. So we have no way of knowing that they're there without actually drilling into them. Well, let me restate that. The only way that we're going to determine that we have those kinds of layers there would be either by drilling or possibly using this resistivity measuring approach with magnetotellurics and audiomagnetotellurics, and look for horizons that are conductive well above sea level. Now, there's limitations on that, but clearly the magnetotelluric data that we got in the saddle wasn't bad. We saw these more conductive horizons that were at high elevation. And when we drilled into them, there was water. So clearly they're useful. They're not kind of a panacea, they're not the be-all and end-all. But they can give us hints that there is water where we don't expect to see it. But it's going to be unique for each volcano, and again, this is new information. We have not ever had this information before, and actually it's only in the very recent past that we've been able to conduct these magnetotelluric surveys. And as I said, we're hoping that we'll be able to actually apply them statewide and see if we can't build a better picture of where groundwater levels are. One of the neat things about the MT is that what we look for is these marked contrasts in conductivity, and we can see very clearly the very resistive horizons. We can see where there's fresh water. We can also see where there's seawater. The seawater, rock that's saturated with seawater, is much more conductive than rock that's saturated with fresh water. So in theory, we could apply these techniques and see the top of the water table and the bottom of the water table. We can see where the transition zone is, because we'll see a big drop in the resistivity at that transition. The resistivity of the salt saturated with salt water is around 10 ohm meters, 10 to 20 ohm meters. Freshwater saturated rocks, we say we're in 600,000 ohm meters more or less. Dry rock is 10,000, 20,000, 30,000 ohms. So we do have some hope of at least beginning that process. And the MT is obviously much less expensive than the drilling. And so presumably we can get some of this resistivity data sort of more broadly around the state, and then go in and drill in select areas to actually get the ground truth. So what I would like to see happen. Yes, ma'am.
Are you finished drilling, or is this an ongoing?
No, we're drilling. We have actually about 2 weeks worth of drilling left to do on the hole that we're currently working on. I'm always looking for money to drill more holes. We're right now doing some surveys, and this is related to your question. We're conducting MT magnetotelluric, audiomagnetotelluric surveys over on the east flank of Mauna Kea. Department of Hawaiian Homelands has about 60,000 acres. And one of the primary impediments to their leasing land is that they don't have a reliable source of water for the ranches up there. And so we've gotten some funding to do the geophysical surveys. If they come back favorable, then we'll be happy to drill a well farm, or drill a test hole for them and see if we can prove out a reliable water source for them. That has been one of the sort of the biggest drawbacks. They have to generate the money to provide the infrastructure for their lessees. And again, a 5,000 foot well is, you're looking at $5 million, and to pump water from 5,000 feet to the surface is very expensive water. We can find substantially shallower water, then it makes it a good deal more likely that they would be able to develop that and then provide that land to the lessees. So, and we're looking to do other work, other parts of the Big Island. We've got a project underway right now that, if it's funded into a second phase, we'll be able to get some geophysics done on Maui and maybe get some insights into what's going on over there as well. Could be interesting.
Do you have any specific locations on Maui that you're kind of eyeing right now?
Right now, the areas that we've looked at sort of most intensively will be on the southwest flank of Haleakala and on the east flank of Haleakala. We actually, the purpose is to try to image the rift zones there. This is a project that's funded by Department of Energy to see if there might be geothermal potential over there. The good thing is we get the information on both geothermal potential and groundwater potential at the same time. So get that information at no additional cost.
Is there a reason your Kona stuff focused on Keabo?
The main reason was that there was kind of a dispute underway over, how the groundwater was being managed over there. And it was
There's a lot of wells there.
there are a lot of wells there. It's kind of a combination of factors. One, the basal groundwater system is pretty fragile. There's a lot of interest in developing the groundwater resources there. And because of the fragility of the coastal groundwater system, there was concern that development of the high-level aquifer could potentially impact the basal aquifer. And sort of as part of that, that's kind of what brought the focus in on that particular area. And so we started looking at I sort of started looking at the chemical and isotopic data in the context of what we had seen both up in the Saddle and in Hilo. And the Kamakana well, when it was drilled, it said, hey, this looks a lot like what you saw in Hilo. And so then started looking in more detail at the isotopes and the age data, and trying to come up with sort of a model that was consistent with sort of the chemistry data, the isotopic data, the water flow data, to see if we could come up with sort of an internally consistent model that could fit all of the data that we have. But it's frequently I use sort of an old aphorism, I guess it's called, in the discussion of groundwater. It comes from the Old West. whiskey's for drinking and water's for fighting over.
Yeah.
And that's kind of what we're doing right now. And of course, the fight is well underway on Maui. A lot of sort of contention over development of any groundwater over there. And ultimately, I don't have a dog in the fight, but I kind of operate under the philosophy that we can't really manage the water resource unless we understand it. And so this is kind of where I'm trying to go. So let's get a better understanding. And in fact, I mean, with this underflow, it suggests to us that rather than trying to access the basal groundwater or even the high level groundwater, if we have underflow going beneath the basal system, in concept anyway, we could actually drill near the shoreline through the basal aquifer, through the salt water, into the deep freshwater system, the underflow system, and have that water come to the surface without having to pump it. Those wells up at high elevation, they still have to lift that water 1,000 feet. The Big Island's water department said that half of their cost of operations is their electric pump. So pumping water is expensive, and if you're lifting it to high elevations, it's way more expensive. So if we could actually develop artesian sources down closer to shoreline, that would save them a huge amount of money. And it would preclude or at least minimize any adverse impacts on either the coastal aquifer or the high level aquifer. Essentially what you're doing is intercepting water before it escapes to the ocean. So you're having minimal impact on the groundwater system within the island. That's kind of the idea.
Anybody else? Okay.
Okay.
I think, one of the things, that blows my mind is how much, hydrologists are like in one camp, geologists are around here in another camp. And just how much of the hydrology tells what's happening with geology. And geologists, traditional geologists don't seem to get it. Understand that. It comes over.
Yeah. Oh yeah.
Fighting for.
Well, both ways. It goes both ways. I mean, the modelers want to model without any real understanding of the geology, and I'm saying you just can't do it. If you don't understand the geology, you can't model the damn system. I mean, it's just, it's not possible. It's a black box. And so, if we understand the geology, if we can access the geology and develop a better understanding. And that's the fun part of doing the drilling, is when you're actually able to see what's going on.
Okay,
Good. Thanks.
Thank you. So next week,